Hi, today the title of my IROS 2020 paper is Exploration Strategy Based on Validity of Actions in Deep Reinforcement Learning. My name is Hyung-Seok Yoon and I am affiliated with the Vehicle Intelligence Laboratory in Seoul National University with advisor Seung-Woo Seo. I am very honored to present my idea in IROS 2020, so let me get started. These are today's contents. First, I will present a brief introduction and then my proposed framework with experiments and then conclusions at last. Most real-world tasks have a continuous and complex state action space. In order to successfully train for such tasks, reinforcement learning agent has to well handle exploration and exploitation trade-offs. Exploration is to try new actions to gather information and reduce uncertainty. Exploitation is to select actions with the highest reward based on gathered information. Dilemma on selecting a single action between two action types is a critical issue. There are some examples below. Real-world autonomous driving, Super Mario game, and robot arm would be representative examples of such complex tasks. Of course, there are many strategies for good exploration. However, some previous methods mainly depend on pure randomness to handle exploration and exploitation trade-off that these methods are incompetent to be applied to real-world tasks directly. To improve this problematic situation, we propose a directed and global exploration strategy that is able to explore environments based on knowledge of the learning process and long-term usefulness of exploration, not just pure randomness. These are key ideas. First, we propose policy selector which measures validity of actions between independent exploration policy and exploitation policy for every step. Second, with individually designed reward, extrinsic reward for exploitation policy and intrinsic reward for exploration policy, each policy is updated with its own reward. Third, policy selector measures validity of actions from the distance of exploration and exploitation policy with callback labeler divergence and its zero avoiding property. There are brief figures. Let's see a figure on the left. There is a car on the roundabout and there are four actions it could act, for example. Action B is selected from exploitation policy, which is the optimal action in such situation, as you know. And action D is selected from exploration policy. With our method, action space A and C has already been searched with exploration policy that in such a situation, action B has high validity to be chosen. Therefore, the policy selector conducts exploitation action. Of course, as the number of training episodes increases, the ratio of exploration action decreases while that of exploitation action increases. Let's move on to the figure right at snapshot 1, 2, and 3. The KL divergence or validity is larger than threshold lambda, so exploitation action is selected. However, at snapshot 4, validity indicates lower than lambda, that exploration action is conducted from policy selector. There is the overview of our method. There is an overall framework for our proposed method and network structure on the right and policy selector on the left, which are our main proposed methods. In addition, there is a formula of discriminator and forward dynamics models which acts an important role in our method. So let me explain specifically. Policy selector, composed of exploration policy and exploitation policy, is able to estimate the validity of actions. It allows an agent to explore based on the knowledge of the learning process and long-term usefulness of exploration that could handle exploration and exploitation trade-off. In figure, the state goes as an input to the policy selector. Then, exploitation and exploration action is selected from exploitation and exploration policy separately. According to the validity of both actions, evaluated by policy selector, A single action finally comes as an output. With this operation, there are 2 points. Point 1. Training independent exploration policy allows our agent to explore with considering the long-term usefulness of exploration. Point 2. Selecting an action based on the validity allows an agent to explore with regarding how much an agent is actually trained. Now, let me explain what the validity indicates in our proposed method. Validity is measured based on KL divergence between exploration and exploitation policy. In addition, with setting the position of each policy in the formula, exploitation policy first, then exploration, it ensures that exploitation policy selects action in the space where exploration policy has already searched or explored. This could be occurred with utilizing the zero avoiding property of KL divergence. Then the formula of policy selector is described. With function f and validity threshold for action selection, a single exploitation or exploration action is selected appropriately based on the validity. Let's see the diagram on the left. As the KL divergence is larger than the threshold, the validity is measured to be high. Therefore, exploitation action is selected. However, when KL divergence is smaller than the threshold, the validity indicates low value, which means much more exploration is needed. Therefore, exploration action is selected at this moment. High validity of actions means that the action is able to extract high return. It also means that an action is started to be selected from exploitation policy, not exploration policy anymore because sufficient exploration has been conducted. Exploration policy and exploitation policy are updated with the data obtained from utilizing policy selector that they influence each other while training. Two policies are individually trained that exploitation policy is trained to maximize extrinsic reward while exploration policy is trained to maximize intrinsic reward. For forward dynamics model, state S and action A goes to an input of the network and next state is predicted. Then, the prediction error with ground truth of the next state is computed as curiosity, which composes intrinsic reward in our model. For discriminator, state S and action A goes to an input and REXP is extracted via comparing state and action pair with expert demonstrations. Then, the reward from the environment, RENV, is added. Then the extrinsic reward for our model is composed. Our proposed method is described on the right. Given threshold lambda and expert demonstration D, we first initialize selector, discriminator, and forward dynamics model. Then, while KL divergence does not converge, which means sufficient validity is not obtained, the below procedures are repeated. Then, it selects a single action with policy selector, then computes the extrinsic reward and extrinsic reward with given state and action pair. Then it updates the forward dynamics model and discriminator, then also updates each policy with its own generated reward. Then the exploitation policy with high validity is the final output of our method. So let me explain our experiments and results. We conducted experiments with 3 tasks: mountain car continuous, Mujoko with Hopper, Hapchita and Walker 2D, and urban autonomous driving with Carla simulator. And I think that many listeners already know about MCC and Mujoko, so let me explain urban autonomous driving tasks specifically. At Roundabout, there are 2 other cars with 1 training agent car. It has to drive toward its destination, a yellow smiley face. An agent should be trained to conduct lane change and right turn at roundabout without any illegal collisions and lane invasions. This is an experimental setup. Performance criteria for MCC and Mujoko is mean and variance of episode reward with 5 random seeds. As MCC and Mujoko has well-designed reward space, we only use expert demonstration in Carla tasks. P1 indicates our first proposed method that employs the policy selector to select policy between exploration and exploitation. P2 indicates our second proposed method that uses expert demonstrations to guide an agent. M1 indicates our baseline algorithm, PPO, and M2 indicates M1 plus P1, and M3 indicates M1 plus P1 plus P2. We try to exclude any individual code-level optimizations for a specific model which are not described in paper, which ensures identical network structure and hyperparameter for all models. This is the result of MCC. We can find that M2 shows better performance, and there is the change pattern of policy distribution on the right. As an agent is trained, distribution of exploration policy and exploitation policy in policy selector changes or diverges as expected. Distance between two policies correspond to the validity of actions. This is the result of Mujoko. We can figure out higher reward mean and lower reward variance with M2. With this result, we can conclude that with P1, an agent could conduct effective exploration that it shows higher performance. An agent could also conduct efficient exploration that it shows more stable performance. Also, we could find big fluctuations in reward during the medium phase of training. With this result, we can know that at medium phase, an agent conducts exploration action mainly that it barely considers environment rewards. We had already expected this aspect of figures. This is the result of the Carlyle experiment. There indicates the main crash spots. We can figure out our proposed method P1 and P2 help an agent to be trained well. With P2, an agent could conduct exploration to a task-relevant region. In an environment with high complexity, pure randomness exploration barely seeks task-relevant space. Expert demonstration helps an agent to explore with directed and global manner. These are the conclusions. We introduce a novel exploration strategy that can conduct directed and global exploration. The main idea behind our work is to consider the validity of the actions by using zero avoiding property of KL divergence. Also, the experimental results demonstrate that our method can explore efficiently with handling the trade-off between exploration and exploitation. Also, there are several future works. We are going to apply our method to off-policy reinforcement learning, such as DDPG. We also plan to demonstrate our method in more complex and various urban autonomous driving tasks or real-world navigation tasks. We are going to figure out the correlation between the validity threshold of action and environment. This is the end of my presentation, and thank you for listening. If there's any question, please contact this email. Thank you very much.